And today I've got a panel of experts to, I'll tell you how to build a star. In fact, they're busy doing it. The question is, the question is whether the energy future will be using nuclear fusion, which is experiments going on. Fernanda Rimini is at JET, and Eurofusion, which is the other side of Harwell, the other side of Wantage, near Oxford. Brian Appleby is at Imperial College, and he works with one of the experiments that set the world alight a bit last November. We've got some amazing stuff. Fernanda's experiment broke all records just over a year ago. Brian's experiments broke all records just a few months ago. And also Stephen McNamara, who's from Tokamak Energy, which is a spin-out company which is trying to make fusion happen faster by doing it privately than waiting on governments to do it all. So what's it all about? I'm just going to turn the lights off. I'm told this isn't going to set the fire alarms off, but if I just quickly strike that, you're all familiar with that, but what you're seeing is oxygen molecules in the atmosphere and carbon atoms in molecules in this piece of wood rearranging themselves, releasing a bit of heat, and lighting the next bit of carbon and oxygen. And that's chemistry, and that's kept us going on pretty well for 600,000 years or something like that. Done a pretty good job of, there we go. That's rearranging atoms. What these guys are doing is rearranging the components of atoms, and that's what nuclear fusion is. Fernanda, do you want to start with Fusion 101?
Fusion 101. Okay, this is, when we say we want to do the same thing. So fusion is what happens inside a star. Inside a star, at the beginning you only have atoms of hydrogen, and then they fuse together and go more and more complex until you make all the ingredients in the universe out of starting from the lightest element. We don't do the same thing. We do something that is slightly simpler because we don't have the space, we don't have the gravity, we don't have the mass. So we use typically things that go very hot, this sort of very thin bundle of atoms that goes very, very hot and not very dense. He does very dense and not very hot. So in both cases, we are not doing the same thing at the start. But what we do, and this is common to all of us, is we choose one reaction, one particular nuclear reaction, which is the deuterium and the tritium. These are isotopes of the hydrogen, and they combine and they form an alpha particle, a nucleus of helium, and a neutron. In a reactor, whether it's the ones that we do, the ones that he works on, what happens is that the neutron goes out, it hits up the wall, and it hits up the water, and that way then you produce energy.
So instead of doing it with burning coal,
yeah,
where you're rearranging the carbon and the oxygen.
And the advantage is that because it's a nuclear reaction, the energy that you produce per unit of matter, per gram, per kilogram, is so much more than what you get from carbon from chemistry.
The only trouble, Stephen, is it's harder.
It is quite hard, yeah. So we've been trying to crack fusion for 50 years now, I think. So we've been making really good progress, but it is quite hard.
Because?
So one of the reasons it's so hard is we're trying to fuse these two particles together, and they really don't want to go together. So they naturally repel each other. So it's a bit like trying to play snooker with magnets. So imagine trying to hit the balls, and all the balls just spread around before they actually hit each other. So in order to get the particles to collide and get close enough where they'll actually join together, we have to make the fuel incredibly hot. So typically we aim to make the fuel around 6 times hotter than the center of the sun. So you can imagine trying to create these conditions on Earth is quite challenging.
And you do it by crushing.
Yes.
Crushing them with light.
Yeah, so when you're trying to do fusion, I guess there are two things. First of all, you need to get it hot enough such the particles will actually fuse together and you'll overcome the repulsion that Steve mentioned. The other thing that you need to do is you need to keep the hot particles sufficiently contained for sufficiently long for enough reactions to happen to get useful energy out. So this containment or confinement problem, you can either do, I guess at one end is what Fernanda does, whereby you're using magnetic fields to hold the particles, which we refer to as a plasma. That's like the group of particles. So you can use a magnetic field to hold the particles in place, and that's magnetic confinement. But instead what we do is we do a thing called inertial confinement, whereby we don't actually actively hold the particles together. Instead, we just compress the entire assembly of particles very rapidly, such that for a brief instant, you've got this very dense, very hot plasma, and enough reactions should happen to get a useful amount of energy out.
And it's been an awful long time coming. Has the wait been worth it? Why haven't we given up?
I think we haven't given up because it has the promise, because it has the promise to release so much more energy than the chemical reactions, and because it does it by not having greenhouse gases, and because despite the fact that it's nuclear, it doesn't have some of the disadvantages, some of the problems of fission. I mean, fission is the nuclear power stations now use fission, which is the opposite. You break a very large atom and you release energy like that. It has some issues. For example, one is that a fission reaction is very easy to start and very difficult to stop. You can have runaways reactions, and they're very difficult to stop. In fusion, as you know, in all of our cases, because you have to heat up the plasma so much, it's difficult to start it, but as soon as something happens, the reaction will stop. So you don't have, for example, the problem of runaways. And that's why we think fusion is the way to go, because it could give quite a lot of power without some of the problems of the power generations that we have now.
Should we go to your experiment then,
Yeah.
Fernanda? So this is, the reason I like it, well, there are several reasons. The dream, I think, is a brilliant one.
Yeah.
But the engineering is absolutely spectacular.
So-
You better give a sense of how big this thing is.
So this is my toy. My line management doesn't like me to refer to it as my toy, but I've been working in fusion since 1987, and this is personal story. I wouldn't still be here if it wasn't fun. So for all of you, research is fun. There are moments when it's hell, but most of the time is fun. So this is the inside of, imagine a donut made of metal. This thing is about 4.5 meters tall and about 3 meters wide. So the width of is the shape of a D, where 4.5 meters, 3 meters wide.
So if you were allowed to go in there, you could have two people standing on each other's
Yeah.
shoulders and a baby or a child on top of that.
Yeah. We don't send anybody in there anymore. We send robots in there.
For very good reason. And this is where your fusion reactions
This is where
happen.
the fusion reactions happen. So as they said, we put in the gas, we ionize the gas because we need ions, and we heat it up. This is the same thing that we do it. Stephen and I work on the same concept, and you use very powerful magnetic fields, because when you have a magnetic field and you have something that is ionized, the particle, if you have a magnetic field going like that, the particle will stick kind of to the magnetic field, and you can confine it, and you heat it up, and you keep it there for long enough. How long depends on how big the machines. The sort of the bigger machines have minute, something like that, between 30 seconds and a minute. We need to go further. He can explain you how you go further.
But
yeah.
I think the next video
Yeah.
picture is, okay, this is it.
This is it. So this pretty pink thing, what you actually see is the coldest part of the plasma. The hottest part the center of the chamber, you don't see it because it doesn't produce radiation invisible because it's so hot. This is the 150 million degrees that we were talking about. So it's so hot that it doesn't even radiate. It radiates in the X-rays, ultraviolet, and whatever, and the neutrons. So
Fernanda, how much material have you put in there? Deuterium and tritium. Is it
oh,
a gram,
grams.
a microgram?
Couple of grams. A gram.
A gram. So that
Probably a gram.
in terms of what that would be in this room, that would be the tiniest spot of atmosphere effectively you put in there.
It's 1 or 2 grams depending how long it takes. But yes.
Whoops, and let's try this one. So this is all dark. What's happening? This is now heating up, is it?
This is heating up. So for a while nothing happens. We're waiting, and then it goes hotter and hotter and hotter and hotter. This is the phase where it's producing because this is an experiment where we actually put the deuterium and the tritium. This is producing real fusion. So this is fusion. This is not just we're not just extrapolating, and it produces the neutrons that come out. We don't produce electricity at JET. JET was never designed to produce electricity, but it produces about 10 megawatt of power.
Is that noise? Is that noise?
The noise. Okay, some of the noises are what happens around, and some of the noises are the magnetic activity inside the plasma itself. The plasma is not stable in the sense that it's continuously dynamically moving, and it makes noise. And it makes noise. Some of the noises we can hear it because they are in the spectrum that we can hear as humans.
But it's basically this sort of hot plasma jelly
it's
shaking around inside there.
And it's jelly and it's shaking around a little bit, and our job is to make sure that it doesn't shake too much.
I mean, you were in the control room.
Yeah.
In fact, I think you were in charge. Is that
Yeah.
right? You were in charge the day
I
when,
was, yeah.
After all these, keep on doing it this way and that way, change that.
Yeah.
I don't know. When you were watching this happen on the screen, did you say, "Oh, this one looks better than the last one"?
This was at the end of a session where we had done it 3 or 4. I think there are 3 or 4 leading up to this one, and every one was slightly better, slightly better, slightly better, slightly better. So we knew that we were going in the right direction, and it was just a question of repeating it enough and getting the last few details right.
And what are you doing? You're sort of tweaking a magnetic field here
You're tweaking the magnetic fields, you're tweaking the amount of power that you put in to heat up the plasma, or the time. You have a pulse that is 30 seconds long, and you need to, I'll put in after 5 seconds, and instead 5.5 and that sort of thing. But this is a pulse that came after the work to get here took a couple of years from the time that people started thinking about these experiments. The first experiments down to this is a couple of years. It's not a few weeks.
And is that because if let's just get that video one more time. Is that going to work? I've got to get back and. At the end of it, it goes all over the place.
Yeah.
And is that because the plasma's sort of busting out?
The plasma is busting out, so it wasn't very happy, but let's say that it's not a very clean ending of the plasma, but nothing. It wasn't a problem.
But in a sense, that's the difference between, let's say, a fusion reactor and, let's say, a coal-fired power station where you just shovel the coal in, you let the air go in, and you let it burn. There's a huge amount of control, and that's the problem.
There is a huge amount of control. That's one of the problems, but we've also made quite a lot of progress on that kind of control. So.
And the other one is, unlike the match, which once you light it, it sort of looks after itself, and even a bad match is some use most of the time. A bad fusion system isn't much good. It's interesting scientifically.
It's interesting scientifically. If it doesn't give you as much power as you want, you will still learn why. One of the important things that we've learned, and one of the reasons why we predicted this. So these experiments, part of the 2 years of preparation of this, was to run fairly complex modeling codes, fairly complex computer codes, and predict what was going to happen. And when you look at the curve of what happened, it goes on the prediction. So that means that we've understood what's happening.
I'm just going to ask, do people prefer it with the lights off? Can you see the screen?
No, not really.
No, let me turn the lights off. So that is the magnetic confinement approach. Essentially, you've just got to keep it together long enough that the heat propagates and so on. As Brian was saying, your approach is just a sledgehammer approach.
Yeah.
But one hell of a sledgehammer.
Yeah, a fancy sledgehammer. So I think I mentioned earlier, we're not trying to hold the plasma in a steady state. We just want to make something that's very hot, very dense, and just let it burn. And essentially, the match, I think, is a good analogy for what we're doing. It's called inertial confinement fusion, our approach, whereby, when you flick matches and you strike them and you get a spark, and that spark most of the time then ignites the entire match head. And that's what we're trying to do in our approach is, we have the fusion fuel in the form of a match head, and then we want to somehow spark it. And the compression is actually the way in which we do that sparking, because essentially as you compress it, you are also making the plasma hot. And I think the analogy here probably is if anyone's ever used, a manual bike pump, and you're pumping up your bike tire and you can feel the cylinder of the pump getting hot as you're pumping it, and that's essentially because you're compressing the air. So we do that same process. We just get something that's a fancy sledgehammer or fancy pump, and by compressing our plasma, we make it very hot. We don't use a sledgehammer, we don't use a bike pump, we use a laser. We use the world's largest laser, which is shown here. And in fact, it's not just one laser, it's actually 192 separate laser beams. So what you can see in this image, the kind of square tubes coming in from the top into that blue thing. The blue thing is a steel cylinder, it's about 10 meters in diameter, and these square tubes are individual laser beams. And there's 192 of those going into that chamber.
You've been here. Have you been?
I have been here. Yeah.
This is on the west coast of America, I should say.
Yeah, so it's Lawrence Livermore National Laboratory. It's about 50 miles southeast of San Francisco. So it's very impressive when you walk around there. And it says in the bottom here, this where you're seen in the photo was used as the set for a Star Trek film in, I think, 2013. So that's the Warp Core from 2013.
How much experimental time do you think that paid for?
I don't know, because that was soon after the laser was sort of inaugurated, so I think it was good PR.
Right, they didn't charge.
Yeah.
But I can't see anyone actually in that picture, because I just can't. I mean, it looks massive to me.
It looks massive, and actually, so the blue, if you see the blue thing going horizontally across, is approximately 10 meters from one edge of the blue cylinder to our sphere to the other. But in fact, all this tech, this is shut away behind steel doors that are about 2 meters thick for when the actual experiments happen, because essentially you have to shield it from all the radiation and neutrons and whatever else flies out.
We'll see the blab
from a fusion point of view, we're not looking at anything here. All the fusion is happening in the center of that blue chamber. So this is just
And I guess this is looking inside.
This
when
is
it was
looking
being built
inside. So this is looking into that chamber. This is the vacuum chamber. There is people in there. This is a very old photo, because nowadays, again, like Fernando was saying, no one goes into this. It's just it's robotics or whatever to actually maintain it. But essentially what you're looking at here is just an empty steel chamber, which is put under vacuum when you do the experiments. But I think that the contrast here, what Fernando was showing was like a donut-shaped vacuum chamber that fills with plasma at low density. What we're doing is we're putting a very small amount of our plasma at the very center of this, and the entire experiment is happening it's about a centimeter in size in the center of this chamber. So we're not filling the chamber with plasma at all. It's only a very small part of it.
We mentioned the lasers.
Yeah.
This is just a small part of it.
Yeah. So this is the big part of the laser. It's a small part of the experiment, but the big So this is just the laser bay. There's 2 of these halls. That's about 150 meters long, and that's just the laser amplifiers to get the energy into the laser beams that you're going to deliver into that chamber. So it's funny that this is the world's largest laser. It delivers about 2 megajoules of energy, but it's based on laser technology from probably the early 90s, simply because, NIF as a facility was, planned in the early 90s. It started building in 1997. It took 10 years to build. So all the technology had to be fixed back then. So you know, if we were to build another version of this, it would look very, very well. It would still look very big and impressive, but.
I mean, it's an interesting point that lasers were invented at the end of the 50s, 1961. I think the first proper laser was built. So this is actually, I mean, the idea of inertial confinement fusion, I think, dates back to the same time. The very first magnetic fusion experiments were being done at the same time. But you think of the transition, how transformational lasers have been in the same time. I mean, that's sort of the technological race, but I guess it's what makes the work you're doing possible.
That's true, yeah, and it's you know, we operate. I think, you know, a lot of fusion experiments, you know, operate on relatively long, slow timescales just because of the magnitude of them and what you're doing. So, you know, if you're a small laser, you can obviously develop much more rapidly, but it takes years here to do it. So.
Here's the target. In fact, even that's not quite the target itself,
yeah. Okay. Now we're getting closer to the actual science.
How big? That's about this big.
So this is about a centimetre tall. This cylinder here, and it's called a Hohlraum, which I think is German for empty room. I don't. Yeah. So I think so. Hohlraum is what it's called, and essentially what this is just. It's like a miniature tin can, but made out of some material like gold or uranium. And what that essentially is it's a way of converting laser energy into X-ray energy. Okay, so I said, you know, we need something to do our compression, and I said laser is what we use to do the compression. But what we actually do is we use the laser to generate lots of X-rays, and the X-rays are what are doing the compression. And our actual fusion fuel is within this Hohlraum.
And it's about the size of a pepper.
A peppercorn, yeah, like 1 millimeter in diameter. So just a very small spherical pellet of fuel.
Okay, so we've got, I think there's this a NIF animation. You can just quickly talk us through these last moments.
Okay, yes, so these red things here are beams of light traveling at the speed of light. Obviously, this is slowed down. And you see here it's coming in through these square, you saw these in the photo at the start, going into the blue vacuum chamber. Your laser light all gets focused into the Hohlraum. And we're going to zoom in on the Hohlraum. And
think of all that energy.
All that energy. And you'll see at times, so you're firing the lasers onto the inside of the Hohlraum, and this is happening in billionths of a second. The laser energy gets converted to X-rays when it hits the inside of the Hohlraum. Those X-rays then shine onto this very small sphere that's the fusion fuel. And this here is where this compression I was talking about is happening. So the compression is happening here. It's getting smaller and smaller. It's getting hotter and hotter. Boom. We should be getting our nuclear reactions here and getting our energy out.
But it's really that sort of, it's this radiation field. I mean, it's quite Star Trek, isn't it? Just
yeah.
inside that thing, and it's just pushing down.
Yeah, that's it. So you know, we're talking about doing compression, but we're actually using radiation, X-rays, to do the compression. Okay, so it's really, you know, you're compressing it by just hitting it with lots of energy on the outside, and then that forces it inwards.
And so it was, well, last November, is it? December?
December 5th.
Some people remember these days very well.
Yeah.
Go on.
So I do, yes, because we numbered the shots by the format of year, month, date.
Yes.
So it was, what was it, 22, 12, 05. So we've been, so I guess there's a contrast between the magnetic confinement approaches and what we do, and that because you're doing it, you know, you just want to spark and to ignite and burn the whole thing. And that means the procedure, it's actually a very cliff edge thing, and that very often you're striking matches and you get a spark, but you don't ignite the match head. And so we've been doing experiments for tens of years where we're, you know, creating sparks but not igniting the match head. But in doing those experiments, we've learned a lot about what is required to ignite the match head. So essentially, last December 5th, there was essentially one where we clearly ignited the match head and we burnt up about 10% of the fuel that was in that pellet. What it meant is that we got more energy out of fusion reactions. We got out 3 megajoules. We'd only put in 2 megajoules of laser energy. So that's like a sort of a benchmark whereby we're getting more energy out of the experiment than we had to put into it to get it going. But from a sort of a science point of view or a physics point of view, what it really means is we've ignited our match head, and now we're kind of creating a different substance in the laboratory because we have this thing that we call a burning plasma. We're now going to be studying that and figuring out how we can make it burn more efficiently, get even more energy out.
And did a sort of an email go around the world saying, "Hey guys"?
Yes, yeah. So we heard informally first from our colleagues at Livermore who were involved in the shot, and we got terribly excited, but then we didn't know who we could tell.
Well, you didn't tell me.
We couldn't tell anyone until they had made their official announcement, is how it transpired. So it was very exciting.
So those are the big experiments. I mean, a NIF, I don't know, they probably don't say because it also does military work. I don't know how much NIF actually costs to build. JET only operates because it's funded by the whole of Europe.
Yeah.
But,
6 billion was the official figure for building NIF, but then the costs of running it are very large as well.
Jet would be 2 billions at today's money.
Stephen, how deep are your pockets?
Not that deep, unfortunately.
So you're trying to go it alone. Tell us about that.
Yeah, so we're using a similar approach to what Fernando described. So we're using magnetic fields to confine a plasma in a donut shape, but there's a couple key differences with our approach. So one is, instead of having our plasma look like a donut, it looks more like an apple. So we're squashing that donut in, and that's something called a spherical tokamak. So this has lots of the same properties of conventional tokamaks like JET, but because it's compressed, it has better stability. So that means for a given magnetic field, you can generate more plasma pressure, and the plasma pressure is what gives you the fusion power. So it's a more efficient way of using your magnetic field, which is often quite a lot of the cost of the machine, building these big, powerful magnets.
You probably can't tell us how much this one cost either, can you?
I think I can.
I think your investors won't mind.
Yeah, they won't mind. Again, we don't really know because there's obviously all the people time that went into it. But I think somewhere around 30 million was the cost of SD40. So yeah, much, much cheaper than the other machines. But obviously that's because it's much smaller. And another part of our approach is, as we said, magnetic fields is what confines the plasma. So we're using a new type of superconducting material called a high temperature superconductor. So I think Fernando mentioned we want to extend the pulse length of these machines. So to do that, we have to use something called superconductors. And these are quite almost magical materials that you can pass a current through it and it doesn't require any energy. So you might be familiar when you turn your toaster on and you look inside, you can see the wires in the toaster glowing red hot. So that's because they're using lots of power and giving off lots of heat. But superconductors, when you put a current through them, they don't require any energy. So these magnets.
This is another one which is, I think, quite interesting, is that it's taken a long time to get to this point in fusion research, but part of it is some of the technologies like these lossless superconductors. So basically, you can crank up a lot more magnetic field without basically melting the magnets.
Yeah, exactly. So that's good for a pilot plant because you effectively don't have to put much power in. So you have to keep the magnets cold. So that's the one caveat with this material. It only has this magical property when it's very, very cold. So normal superconductors are 4 degrees Kelvin, which is incredibly cold. So 4 degrees colder than it's absolutely possible to be.
So, I mean, this is the cutaway for the inside, but I think we could go straight to. So we've just missed an anniversary for you.
Yeah, it was yesterday. Yeah, so this time, probably actually about this time of the day, yesterday, a year ago, we hit one of our big milestones on SD40, which is our current machine, and we got a plasma temperature of 100 million degrees in the center of this device. So the thing that's really kind of amazing about that is, unlike JET, SD40 the plasma is about this big. So in that plasma, in the center, we had a temperature that was 6 times hotter than the center of the sun.
And just a short distance away,
yeah,
you've got these superconductors.
Oh, so SD40 doesn't use the fancy magnets.
but
yeah, the wall is pretty kind of normal temperature, so like room temperature.
You could, in principle, touch it if you did.
Yeah, you wouldn't want to go in there when it's firing. But yeah, you could touch the wall and it would be kind
what
of.
What sort of feat? Yeah, I mean, that's again. It's been a shorter journey for you.
Yeah, so we Tokamak Energy formed 10 years ago. So some of our founders kind of span out from the Culham lab. And yeah, since then we've grown. So now we're about 250 people. And SD40's been around.
To see that, is that the moment you think, okay, we're on the right track?
Yeah, this is one of our kind of big milestones. The idea was to really prove the concept of the spherical tokamak and demonstrate that it can generate fusion-relevant temperatures.
Okay, proof of principle. What about the future? JET is
closing.
It's been going since.
It's been going for 40 years. In June 2023, it will celebrate 40 years since, if we manage to get it to then, 40 years from its first plasma.
It's put in good service.
It's been put in very good service.
this is...
Is that just because the life of the machine has come to an end, or
No.
investment?
It is complicated as usual. We are moving on. The whole world is moving on to other things. I think Jet still has quite a lot that could give, but we also have a pool of people, pool of resources, a pool of money that is limited. So we had to take decisions, and decision was taken at the European level and also at the UK level to finish it.
I think you touched a sore point there.
No,
mate. We
I
can't
think
fund everything.
you can't fund everything, and it's true that a 40-year-old machine, you never know when it breaks, and it would be possible to repair it, but it would cost maybe too much.
So instead, this is the one they're now building, not just
This
Europe.
is the one. This is not just Europe. This is 7 international partners, and I think I'm right when I'm saying is 80% of the world GDP. It's Europe, Russia is still in, US, India, China, South Korea, and Japan. So it's basically everybody. And they're building something that it's, it looks very much like Jet. It's not random. The person that designed, the people that design it were mostly coming from Jet or from that generation. So again, is the donut rather than the apple with the cork out, and it's 10 times the volume of Jet. Huge.
So I was going to say, you can see there some people.
Yeah.
It is absolutely phenomenal, and it's taking a long time to bring together. This is a picture from just a few weeks ago, I think, with these. So presumably those D-shaped things are going to be a bit like that.
Yeah. So the inside will be fairly similar to Jet if you look at it, apart from the fact that it's twice as big in every dimension.
And why does that help?
And it's got the superconducting magnetic fields. It's the old superconducting magnetic fields which have to be really, really cold. So it's not the brand new one fancy that they're using, but at least it can achieve longer pulses.
I mean, if you're on social media, it's worth following ITER.
Oh, ITER is wonderful. The
put out these pictures.
Instagram feed of ITER is gorgeous.
And
Like the flybys.
they know it.
When they fly over the site.
When they
They're
fly
really
over
there.
the site, when they transport all these things. One of the things is that the components of the donut, the magnetic fields, everything has been produced within the 7 partners, and it's driven or is taken by boat to France. So.
And then, yes, and we see those amazing
And we see
pictures of
those
things
amazing
being
pictures.
driven up the road. And then this is the full construction site.
Yeah.
It's just mind-blowing how big, and it's the plan is that it starts.
We don't know exactly, because one of the things is when they started putting it together, they found some defects in fabrication. Again, fabrication, you couldn't test everything, so they think there will be a little bit of a delay. It was supposed to have first plasma in 2025, by the end of 2025. There will be a delay, but they haven't said how much.
But that's partly just because it's so big and.
It's so big. It's an engineering. So I hope one of the things that you get out of what we are all saying is that these are not exercises of white people in lab coats with a beaker and drawing things on a whiteboard. These are major. These are huge engineering, fairly complex. Even if we talk about a more compact machine, they're still extremely complex from the engineering point of view. So. It's not surprising.
I saw some of that a few years ago, and it's also very precision. I mean, that's one of the other things. It's these huge components, but they have
need to
be
go
made.
within millimeters. And
So I did actually get to go there 9 years ago, and this was an absolutely empty hall at the time where they were going to put together some of those magnets. I don't know.
I think all the magnets have arrived by now,
Yeah.
so they are putting them all together.
But that was the crane that was supposed to be carrying them, me underneath with my tape recorder. But it is mind-boggling. I don't know how easy it is to visit the place, but I do recommend at least going to their website. Stephen, those shapes look familiar.
Yep, so these are the kind of famous fusion magnets that we're all familiar with. So yeah, all tokamaks have similar, these D-shaped magnets
But this
that hold
is
the plasma.
you're working on the next step here.
Yeah, so this is part of our magnet development program. So as Fernanda said, we're using a new type of magnets called high temperature superconductors. So they can operate at higher temperatures, they can carry more plasma current, and they can operate at higher fields.
And this is what the testing phase. So you're trying to iron out the problems which ahead of time before you start putting things together.
Yeah, so this is really a demonstration that the magnet technology can work in a kind of an integrated environment. So where when we turn these magnets on, they all interact with each other in quite complicated ways. So by building a complete magnet system, we get to see how they interact and really kind of understand and importantly be able to model how the magnets behave so we can then scale up.
I mean, will you be doing experiments on these? Will you have sort of crocodile clips, or I don't know how it works on there, and beam me up? Or something?
Yeah, sort of, not quite crocodile clips. Yeah, the whole thing will be in something called a cryostat, which keeps it very cold, but there'll be wires and sensors coming out of it. And we'll be doing lots of experiments where we turn the magnet on, turn it off, kind of turn it off and on quickly, just to see how the coils behave.
But that's the work of a fusion scientist. It's all sorts of.
Yeah, I think that's one of the things I really like about fusion. It's such a diverse kind of community. So to make a fusion reactor, you have plasma physicists, engineers, electrical engineers, chemists, material specialists. There's so many kind of skills that have to come together to build a fusion plant.
And so they started talking about ITER about the time they had agreed to build JET, so in 1977. Took them 6 years to build JET, took them 30 or 40 years to build ITER.
I think they agreed ITER as part of because it's an international, they agreed as part of the famous Reagan-Gorbachev meeting in
1984.
Reykjavik?
Reykjavik,
Reykjavik.
yes.
And the sort of the myth is that Reagan came home convinced that they had signed to build this thing. No, that's when they started putting together the team and then designing. And then once they had a design, one of the main partners, I'm not going to say which one, pulled out. And thinking that the whole thing would fall, instead the whole thing didn't fall, so they just made it slightly smaller, and then this major partner went back in and said, "Oh, now you redesigned it, and we're happy." So, yeah.
They don't wear cowboy hats. Those partners do that.
No, they don't. I'm not saying anything.
But a lot of the design work was done at Culham, I think.
A lot of the design work was done at Culham, and then a lot of the people came from Culham and from JET.
And why was I asking that? Okay, because your timeline is quite different, Stephen.
Yes, that's right. So yeah, I think our timeline is quite bold. So we think in order for fusion to have an impact on climate change, it really needs to be ready kind of by the mid-2030s. So we've devised this kind of roadmap to get there. And I think one of the key elements is because we believe we can make more compact devices, that allows us to go quicker. So instead of it being a kind of multinational, kind of 80% of the world GDP, it's kind of small enough that a single company can build one of these things kind of on their own.
And so ST40 is the one that you were showing us earlier.
Yeah, that's our current machine.
ST80 is the next one. The magnets we were looking at, are they sort of prototypes for the magnets on that, or what?
Well, sort of. So they're the same technology, but they're a much scaled down version. So ST80, the 80 refers to something called the major radius, which is kind of half the size of the plasma. So it's double the size of ST40.
So 80 centimetres?
Yeah, 80 centimetres.
Right.
And I think JET is 3 meters?
Major radius is 3 meters.
Yeah, so it's about a third the size of the JET machine.
So how much of ST80 exists at the moment, or is it still?
None of it exists at the moment, so we're still in the...
You've got 3 years.
We've got a lot to do. I better get going after this.
Thanks for sparing the time to come to talk to us.
Yeah, we started...
I don't know, is it quite exciting to have that kind of timescale?
Yeah, it's very exciting. I think it can go from stressful to exciting, but we kind of recognise that we need a bold vision, and it kind of drives everyone forward. So we've recently signed the site agreement, so we're going to be building this machine next to JET. So that's very exciting.
And then, even while you're doing that, you're going to be planning what you say here, early 30s, a fusion pilot plant. So that would be what? That would have the kind of fusion plasma that you could make energy with. Would it have the stuff that would actually generate electricity off the back of it?
Yeah, that's the idea. So it's sort of similar to ITER in that it would have kind of the mechanics around it to extract the energy, and we are hoping to kind of actually turn some of that into electricity. But I think one of the benefits of a private company, we can take a bit more risk. So we can start the next program before we've finished the old one. So that's what we did with our magnet technology. When the company was formed 10 years ago, you couldn't build magnets from high temperature superconductors. So instead of waiting until we developed that to start the next project, we just assumed that it would work and kind of started everything in parallel. Yeah, and now it's all come together. But again, I think that's where private industry can do that. Obviously, government labs can't.
Do your investors sleep at night?
Yeah, I think they're quite excited by the opportunity.
Okay, so let's see what's next. Okay, so Brian, you wanted to tell us about yet another version.
Yeah,
of all this.
well, I'm not sure if it is another version, but I guess just going back to what I work on is ICF, and I was showing these images of the world's biggest laser, but then I was pointing out, well, the laser is just a sledgehammer. It's what we refer to as the driver. It's the thing that sends the energy in order to get the ignition of the fusion fuel. And so really the great thing about lasers is they deliver a precise amount of energy in a very short time. But there are other ways in which you can do that. And so another approach is that instead of using the laser as a driver, you can use magnetic fields as the driver. And that is basically what we refer to as magneto-inertial fusion, as illustrated by this pretty cool image from the Z machine at Sandia National Laboratories in the US.
We'll come back to that one in a moment.
Yeah.
This is the
concept.
process
Yeah. So what you're doing, so again, it's about 1 centimeter tall. And what this is a cylinder filled with your fusion fuel. But then those grey circles on the leftmost image, they are magnetic field lines. But those magnetic field lines, it's still different to magnetic confinement. They're not holding this thing in place. Instead, what they are going to do is they're going to crush it. Essentially, you deliver an electric current very, very rapidly, generates extremely large magnetic fields, which then crush this cylinder, and that's what you see happening in this sequence. So there is about 25 megaamps of current being delivered to that 1 centimeter tall cylinder. I think.
Don't try this on a Coke can.
Don't try this on a Coke can. Yeah, like standard kitchen appliances take about maybe 30 amps or something. This is 25 megaamps. The magnetic fields you get are about 10,000 Tesla, which is quite large, and it's essentially just doing a process whereby in about 100 nanoseconds, so that's 100 billionths of a second, it's doing that compression. And the red stuff you can see in the rightmost image is hopefully our fusion fuel, which has got very hot and has started to burn. So that's the scheme. This is on the 1 centimeter scale. If we go back maybe to the image before, this is the driver that is delivering that very large current to the very small place. So it's very similar to the laser in that you have this huge machine that's the driver delivering all the energy to a very small location. So the diameter of this image is about 30 meters, and all around there's a ring around the edge of that contains a whole bunch of capacitors that store electrical energy. Those capacitors all discharge the energy at the same time, the 25 megamps. It flows through what you're seeing here is the blue stuff is basically a tank full of deionized water with some tubes going through it which carry the current into the center. And then buried in the platform at the very top of this image is where you're located, your 1 centimeter tall target.
Where is it?
Yeah. Inside there is a chamber, a smaller version of the vacuum chamber that we have at NIF, and in the center of the chamber is this 1 centimeter tall target. This image looks cool simply because this is a large amount of electrical current that's delivered very rapidly, which just sends out an electromagnetic pulse, which causes that cool lightning effect across the top of the water.
I think we all want to know, was this a good day or a bad day?
This is a pretty good day. In fact, this image is quite old, and you can't actually take this image anymore because for health and safety, they put a platform across the water. So I think this image is about 10, 15 years old, and you won't be able to get such a good one. But this is good because it shows that we're delivering the electric current. So I think what I wanted to bring this up to kind of emphasize that there are many approaches to fusion, and we've seen different magnetic confinement approaches, and then I've said, well, there's inertial confinement, and within inertial confinement we have different ways of doing it, and at the end of the day it comes back to this thing of, well, can you get your fuel sufficiently hot and then confine it for sufficiently long to get the reactions to happen? I think we have these inertial confinement fusion approaches. What the private companies are also showing us there is a multitude of different ways of doing this as well with magnetic confinement.
And there's a lot of them, isn't there, Stephen?
I've lost count, but I think there's over 30 now. And I think last year there was $5 billion invested in private fusion, which was the first time that there was more money in private fusion than public fusion. So it's
Can
really
you all
exciting.
win?
I don't think we can all win, but I think there can be different approaches. So fusion has lots of applications. So there's kind of energy production, which we're probably all familiar with. There's also heat production, making hydrogen. You might want small devices you can localize. You might want big devices. So I think there's lots of scope for several different kind of routes. Just like now, we have different ways of making energy. We have wind, solar, gas, coal. I think it could be a similar thing with fusion, where we have magnetic confinement, inertial confinement, magneto-inertial confinement.
I think it's possibly also worth adding from private companies. There are also some private companies that are doing fusion from the point of view of things like space propulsion and maritime propulsion, so it's not strictly about energy.
Whoops, and now, Fernanda made us all sad by saying that JET was closing, but that's not the end of fusion in this country.
One of the exciting things is that in the last 10 years we've had the private companies, but also some private-public partnerships, and the UK government has actually decided to go alone and build a reactor that will put. The aim is to put. So if you want, the aim is really to put some electricity on the grid by 2040s. The design is fairly well advanced by now. It's called STEP. And in October there was the choice of a site in Nottinghamshire. So it's an old coal power station that has all the right infrastructure. So it's West Burton. And last week the government established what is called the UK Industrial Fusion Solutions. So it's the company, it's the government branch that will deliver the construction, and that is also why we need to close JET, because we need the people to work there. And so it's not going to be a Callum. It's not going to be here in Oxfordshire, but Callum has this sort of cluster of activities that go from the fuel, from studying the fuel to studying the magnets to studying the materials, and sort of it tries to approach the fusion reaction, the building a fusion power plant from all the sides that are necessary.
I mean, it's been a long time. We've said this before. Stephen talked about whether we could help with global warming, and I suspect a lot of people here are thinking, why not spend all that billions on solar panels and on wind farms, because they're already displacing greenhouse gases. I mean, you obviously believe in it, Fernanda.
I believe in it. It's not just a question of believing it. There is the need for the renewables have their place. I think the future is diversifying the energy production and going towards electricity for all sorts of reasons, hydrogen, whatever. And amongst the diversity, you will need something that provides the base load, that provides the energy, the electricity production, big for factories, for this sort of usage. And I think this is where fusion could fit in terms of where we need. So it's the kind of thing that at the moment we are doing. The moment we are doing it with gas, we're trying to replace it with fission. As we were saying before, fission is not as desirable. It's got some aspects that are really not terribly desirable. So this is why we would like fusion to replace essentially the big power stations.
I mean, I don't know if people up here are thrilled by what they've seen, be persuaded. I don't know if I've got a microphone here, if anyone's got any questions or thoughts. Yeah. Oh, sorry.
Just a quick question. You said 100 million degrees. So just wonder, how do you, are there any material which doesn't melt?
That's the question we skipped.
That's a good question. So that's kind of why we need these devices, because you can't just hold a hot plasma in a tin can. You need some way of, so in magnetic fusion, we use the magnetic field to pull it away from the walls of the machine. So it's not actually in contact with anything. It's sort of suspended in midair by the magnetic field.
And if you think about it, the comparison would be, I don't know, having a rusty nail and trying to hold it in place with 30 bar magnets. In a sense, it's not simple to keep it in the right place. Go on, please.
Thank you. We all know that nuclear power stations are perfectly safe. We forget 3 Mile Island and Chernobyl. Is there any likelihood of any problems with any of your?
That's a good question. Yeah, I think that's one of the advantages of fusion, is that it is kind of inherently safe. So as Fernando was saying, it can't run away. So a fission reaction, you're trying to kind of calm it down almost and stop it running away. A fusion reaction, you're desperately trying to keep it going. Any disturbance, it will turn itself off. So there are some hazards.
I think of it being a bit like a match flame in a gale.
Yeah, you're trying to desperately shield it from the wind. So there are some hazards, but I think we like to think of it more of a kind of an industrial plant or a chemical plant. So there are kind of things we need to be mindful of.
No, there is some radioactivity because we are dealing with nuclear. It's not that long lasting, and it's not as easy, for example, to use for to make weapon or to weaponize.
You're not getting plutonium out of it,
no.
for example.
And some of the aspects already we have to manage them at JET, because as soon as you start going into deuterium-tritium fusion, you have to manage all the aspects. So we do have already some experience.
Could you explain how you get energy out of these machines? I can see you generate a lot of energy, but how do you actually get it to make electricity? Presumably you can't sort of put a water jacket around
Yes,
the
you do.
walls.
Yes, you do.
Amazingly.
It's cooling. So all the machine will cool. So you slow down. You will slow down your neutrons, and then you will have a cycle that from that heats up the water and steam. That is the raw thing.
I mean, I find it incredible, this idea that when that plasma's actually going, it's just flooding the walls with these high-energy neutrons. They're smacking into the walls.
Yeah.
That's heat. That's the heat that you actually have to take away, I think.
Yeah, you will have to take it away. At the moment on the present machines, we just take it away and we do nothing with it. It will feed. It will be a steam generation. There are some sort of. This is where I call the holy grail of fusion, where some of the reactions could produce electricity directly, but they are very difficult, and we are not really, apart from one private company, Helion.
Yeah, Helion. Yeah.
Helion, they are trying these reactions too.
Just a supplementary. Do the neutrons degrade the material of the reactor?
Yes.
So
So
they
there is
have
a
life.
part of the studies are the material studies on how to find, for example, stainless steel that can tolerate the damage of the neutrons, and you don't have to replace it every 6 months.
One of the reasons I was really keen to do this talk, we've had all these breakthroughs just in the past year, which I think have been so thrilling. But also, this is all. There was a NIF-like machine. I mean, I think it's still there at the Rutherford Appleton Laboratories, just down the road from here, called Vulcan. These are local experiments. I think it's just thrilling that this stuff is going on our doorstep and people can sort of almost go and see it. Certainly I'm hoping someone will go and try it at some point. But there's one other aspect to this, which makes it even more local to us in Swindon. This is a press conference 65 years ago, when the first of these toroidal machines big toroidal machines was being run at Harwell, again, so very local to us. They got 5 million degrees in the centre of the plasma, which was pretty extraordinary at the time. They also got neutrons. They made a mess, sadly, of how they interpreted the neutrons. It was both good and a bit of an embarrassment. But that's the zero energy thermonuclear apparatus. This is one quadrant of the machine, which is now at the Wroughton Science Museum site. In fact, it's been there for a long time. This is where it was at Culham. That's one of the buildings at Culham back then. I don't think you get people sitting inside used bits of nuclear fusion reactors these days, but that gives you a sense of the size of that thing shortly before, and I think that is identical to this one here. It's the same thing. I don't know what happened to this quadrant or whether it's a slightly different part. They've also got, there was a model at Culham years ago, a scaled down model, which they've got there. So an important part of fusion history is just up the hill from us at the Science Museum. They told me it's not on display, but I'm sure we can campaign to change that. And I think with that, unless anyone's got any more questions, we have, yeah.
How practically small could you make a fusion reactor? I mean, are we ever going to have fusion-powered cars or aircraft, or do they just have to be too big?
Unfortunately not with the current technology. So they still need to be kind of reasonably large. So our envisaged power plant is about the size of jet.
Yeah.
So it's kind of 12 meters across, 12, 15 meters.
Say that you couldn't make it any smaller.
Yeah, there are bits in the physics that say that you can, but there are people that think you can put it on ships, for example, because that is a big container ship would be big enough to have that, and spaceships, definitely.
As we look to scale this up, how readily available is the fuel that we need to burn?
Yeah, that's a good question. So the two fuels we use for deuterium and tritium fusion are deuterium, which comes from seawater. So I can never remember the fact, but it's something
One
like,
out of 6,000.
Yeah, and I think this much seawater would be enough to power Swindon for 10 years or something. I can't. It's something ridiculous like that.
It is. It is. I mean, that's one of the sites you don't need a coal truck. If you remember when the coal trucks used to go to Didcot Power Station, you'd just have these endless trains, and they'd keep the place going for a day or two or something.
Yeah, and then the other fuel is lithium. So tritium doesn't exist in nature because it's radioactive, so it decays away. So we make tritium from lithium, and again, I think the lithium in the battery in your phone plus the water in this bottle is all we need to kind of power Swindon for a while.
So you said we could use the lithium, the same lithium in our phones. Would we be able to recycle the lithium from our phones and then use that for the power?
That's a good question. I've not really thought about that. I don't see why not.
I mean, you would. I think the point is you can get the lithium very easily. Despite what you might be reading in the papers, lithium is quite easy to get hold of. You can also get lithium from the sea.
Yeah.
It's a tiny.
You can also just use deuterium as a fuel, and that would produce energy. It just produces less energy than the deuterium and tritium combination, and requires a higher temperature to get it going. So we're not restricted to deuterium, tritium. It's the easiest.
Yeah, that's what
I mean, in short, it costs you, in terms of fuel, it costs you almost nothing. It's not dangerous. It's not going to pollute the atmosphere. The only trouble is it's hard.
Yeah.
Just as an aside, you said about the Wroughton Museum. I asked the guys outside earlier today. They're hoping to have it open next year. And if anybody's ever been at the Science Museum at Wroughton, it is a bloody fantastic place to go. So hopefully it'll put Swindon on the map once it's open.
Absolutely. In fact, I think the next talk in an hour's time is from Laura, I've forgotten her name, I'm sorry, but from the museum, talking about some of the stuff they've got there. So I'd recommend people to come to that. If anyone's got any more questions, what I really want is some of the younger people in here to think, okay, I mean, people can go to Colum on a school
People,
visit.
we have open evenings once a month. I don't know how you apply, but if you go on the Colum website, they can tell you how to apply and you can visit.
And we're starting a STEM outreach program, so we're trying to get to kind of schools in the local area. So if you're interested in maybe a talk at your school, then you can get in touch by our website.
Do you offer apprenticeships?
Oh yes,
Yes, we do. Yeah.
In what specific?
Everything. Everything.
Physics-based or
No.
maths-based?
No,
The apprenticeship in
Engine-
robotics. as well.
Robotics, engineering, all sorts of things.
I don't think you could get a better apprenticeship than at some of these places. They are amazing and they have such good people. You going to fly anyone over to California for us?
Come study physics at Imperial, I think is what I'll say.
Okay, that's brilliant. Thanks everybody so much. I've lost the sign now. It had all the credentials up there a moment ago. Thanks very much for coming. Thank you, Fernanda, Stephen and Brian.
Thank you. Thank you
For
very much. Yeah,
keeping
thank
us
you.
informed.